from Gary that jog your memory. And I started working with Gary about 10 years-ish after Keith did, and the same way that Keith did. I think Gary was a little bit upset to find out that I was a student and not a postdoc, but that was probably part of the Schramm phenomena, I think. He left the details out sometimes. And I saw some of Gary's handwritten notes, and Gary never accepted the fact that there were modern ways to communicate, even after the invention of email and cell phones and stuff. The way that we used to work, I wrote about 35 papers with Gary, and I would come in early because Gary didn't, and work on some calculations or something. And the first time that we wrote papers together, I would produce a new draft by the afternoon, and Gary would come in and then come back upstairs after teaching, and I would go home at 5:30, or hard to believe that I would go home at 5:30. I don't quite make it to 5:30 sometimes these days. And I came back, and the whole paper was gone. There was no tech draft anymore. It was a handwritten version of the paper that Gary would leave me in the morning. And it looked just like that. And I think for a long time he hand wrote many of his papers because that's the way he liked to think. So finally I was like Keith, I gave up trying to write the paper and just let Gary write it the way he wanted to, because it wasn't going to survive one edit even. So that was an interesting part of life with Gary, and something that I'm sure that's the way he thought about things carefully, but there was no change between what Keith showed from 1981 or so and what I saw in the 1990s. They looked identical.
I think what you also lose now is the handwriting, because handwriting tells you something about a person.
Yep.
And you also knew Gary from his handwriting. I mean, if you see that, you recognize it. And now with email and everything, we don't write letters to each other anymore.
No, we don't want to do that. Our next speaker today is Mike Turner, who's no stranger to either one of our departments. He's visited here 5 times or so, maybe, since the new building, at least since I've been around. He's currently the emperor, he tells me, of the Kavli Institute for Cosmological Particle Astrophysics or something like that. Cosmological physics. I got that wrong on purpose. The first time I remember seeing Mike and Gary together is in the 80s sometime when I was at Fermilab, and we had a basketball team at Fermilab that was called the Hematomas. And the league had nothing to do with scientists. Rocky Kolb and I were one of the few scientists that were allowed to participate, and we actually won the league several times. And that attracted Mike's interest, and so he bought a majority share of the team. And we were having pictures taken in the lobby with the trophy, and Gary was standing up. Mike probably doesn't know this, but Mike was down there holding the trophy in some ridiculous pose with Rocky and I. And Gary was standing up at Fermilab in one of the glass areas, looking at Mike with like the look that he was giving Keith when he wasn't very happy. And so they had certainly crossed styles in the way that they like to do physics. I certainly met them many times in Aspen. They were both legendary volleyballers there. I saw Gary leave the court many times very upset. And I think one of Mike's most interesting collaborations was with Gary and L. Lawrence Krauss when they wrote a paper about the flatness of the universe. And in spite of piles of observational data that contradicted their conclusion, they reasoned that it would be better for theorists if the universe was flat, and wrote a very nice paper then. It turns out today the universe is likely flat, and I enjoyed that paper, and I know Gary did too. Today Mike is going to talk about his friend Gary and how they shared in starting the particle astro revolution. Thanks, Mike. Oops. Where's the final one?
else I have to do?
Which cable did you use?
The HDMI?
Okay, so we just have to push a button on this.
Oh, okay, great.
Let's try again.
Oh, there we go. It looks like it worked. Well, I'm honored to be here to help remember Gary. And so I'm going to talk about Gary and cosmology and tie him to the current model, Lambda CDM. And as Keith was mentioning, there was this meeting in Madison, December 1978, on proton instability put on by the great impresario David Klein. It really was quite a spectacular meeting, which maybe we can talk about at lunch. And that's where I met Gary. And he was really, doing more cosmology than he was. He gave a talk on the matter-antimatter asymmetry, which I'd like to revisit. And so if we did a word cloud for cosmology today, these would be the words, or among the words. Dark matter, inflation, dark energy, WIMPs, baryogenesis. I think we've heard a lot of these words. Cold dark matter. Gary had a difficult relationship with cold dark matter, which I'll come to. And thousands of physicists and astronomers working together to figure it all out. And so, particularly for the younger people, you might think, well, that's the way it always was. There it was, cosmology, but it wasn't. So I thought I'd start out with a brief history of cosmology. Ooh, that gray is, okay. Can you tolerate that color? I could change the colors. Okay. And of course, the universe is enormous. And so the universe is often beyond the reach of both our instruments and our ideas. And so in this history, I've kind of put both ideas and theory, what led. So general relativity, 1915, about 100 years ago, that's the framework for even discussing the universe. Without it, you can't discuss the universe. And of course, these two are data. These are Hubble's discoveries that the universe is expanding and had a beginning, and there are other galaxies. And then there was a slow period. The other thing about cosmology is it's boom or bust. There was a slow period here, and I put in this period the theorists catching up and understanding the expansion, and that's a very interesting story about, is the expansion real? And also Gamoff's paper, which Keith alluded to, and I wish I had more time to talk about this. I'm going to write, if I were still writing for the reference train of Physics Today, my next article was going to be on explaining Pauli's comment about that paper wasn't even wrong. And what it was going to give is an example of wrong papers that have been so influential. And of course, Gamoff's paper didn't have a correct equation in it. And actually, I have a small quibble with Keith. They didn't even predict the temperature of the microwave background. But it transformed cosmology. And then the discovery of the hot beginning, that's microwave background, physicists became interested. And then, probably 80 is too precise here, but the era of big instruments and big ideas. And so I put both theory and data, and that, I think, has boosted cosmology. So Gary got his PhD at NYU. When we were writing his obituary, we were thinking about, well, let's see, the standard way is you get your PhD under someone. That's the term of art we use, and that under person would be Mal Ruderman. But Gary never worked under anyone. So we found alternative phrasing, I think. So he got his PhD in 1968. What did cosmology look like? In 1968, high redshift was a few for galaxies. Around 1968, the highest redshift quasar had, actually, Pat remembers this, the highest redshift quasar had probably jumped from about 1/2 to 2, and it was on a very steep curve. And so there were less than 1,000 redshifts measured in total, and the idea of a redshift catalog, there wasn't such a thing. The CMB had been discovered, I mentioned that earlier, but the spectrum had not been established. The Wien turnover had not been, 5 years earlier was the birth of relativistic astrophysics, which completely changed astronomy. Relativity used to be boutique science, done by mathematicians, and real astronomers don't need to worry about it. But 1963 changed all that. Quasars, neutron stars, I guess I should have put that, by that I meant pulsars, the microwave background, the chronometric, the first Texas Symposium on relativistic astrophysics, and the birth of David Weinberg. So this is for Gary. H naught, and this is important for the students here. I hope you all know the difference between precision and accuracy. So the Hubble constant was very precisely known, but it was not accurately known. And okay, and more importantly, cosmology was the province of 30 or so astronomers led by Alan Rex Sandage. And so we ought to hear what Alan has to say about it. So he wrote a very influential paper in Physics Today where he defined what cosmology was. It was a search for two numbers. Do I have them? Oh, H naught. How many people know what H naught is? Everybody. How about Q naught? Not so many people know what Q naught is. And the 200-inch was going to solve this. The 200-inch telescope was going to clarify what he called was our world model. And as I said, it was really tens of astronomers working, and I don't think they were working together. Pat, did I get that right?
No, they're definitely not together.
They were not working together to figure it all out. And I think I first heard this quote from Gary, maybe not. Landau on cosmologists, often in error, never in doubt, but always entertaining. And I guess another way, all hat, no cattle, for those of you not from Texas, so it's all hand-waving, no data. Okay. The 1980 revolution, somewhere around 1980, things really changed when the deep connections between quarks and the cosmos were recognized. And Gary was part of that revolution. You know, here's the convergence of the coupling constants. This was very, very hard to find. I should have looked at Paul Lanneker's papers, because the coupling constants really did converge at 10 to the 14 GeV within their error bars, which were not that big. And that's why we were all up in Madison, because it looked like SU5 was going to solve everything. And we've heard a little bit, from Bob Scherer, baryogenesis, the idea that the universe generates a baryon asymmetry, and it involves gut physics, violation of baryon number, and CP violation, all kinds of great ideas, cosmic strings inflation. One thing that Gary was involved early on, I'll come back to this, is the fall of the Hadron Wall. So I don't think he can take credit for the Berlin Wall, but the fall of the Hadron Wall is very interesting. Let me just go back. I'll show you this paper later. There was a time, and in fact, if you go to Weinberg's book on cosmology, he talks about you're not able to talk about the universe earlier than 10 to the minus 5 seconds because it's a soup of overlapping, strongly interacting hadrons whose mass spectrum is rising exponentially, so you can't even define the temperature. I think I got all the right words in there. And once you know that the proper degrees of freedom are point-like quarks, it changes everything. And so, let's see, the Hadron Wall would have been right about here, and it opens up, so here we are today, opens things up to speculating about the baryon asymmetry and inflation and all extra dimensions, all kinds of interesting things. So that's from the theoretical side. The 1980s, I think we might characterize them as the go-go junk bond days of early universe cosmology. So there was no data. So you could write a paper on anything, and it couldn't be proven wrong. And actually, one of the examples, I have to mention Dave Schramm. I came to Chicago, and he had just written a paper with Jim Latimer about the collision of neutron stars being the source of the R process. And I thought, oh my God, they'll publish anything in Okay, so bold ideas are important. And we've heard that Fermilab was maybe the mother church. So, yeah, maybe that's not fair. Does anybody remember Church Lady on Saturday Night Live? Some of the older people do. So Gary played an interesting role, and I think we really heard it. He was a steadying influence. He was the connection to astronomers. So his appointments were in astronomy departments, at least before he came to Ohio State. And I think I can't really add to what Keith and Bob said, but he sweated the details. He thought data was important. So let's see, here's inner space, outer space was this big meeting at Fermilab. I should show the table of contents. You can see Lambda CDM right there. Of course, Gary was a speaker, and paper prominently featured there. A lot of people don't know that inner space, outer space, if you can read this, was the official conference of the 1984 Summer Olympics. I take some pride in this. This just doesn't involve Gary, but a side story. We got the University of Chicago Press to publish the proceedings, and we offered it to them, and they said, well, we don't publish proceedings, we're a scholarly press. And I said, well, this is not a proceedings, this is a milestone. And Pat Osmer's shaking his head yes. So we got, and then I'm surprised, maybe at lunch we'll talk about the first Texas in Chicago and the famous food fight that Gary was involved in. Grant is laughing, so Grant was there. So bold ideas. Lots of ideas and not so much data. And I think there was a fear that, this was like a hot air balloon with no ballast, and it would just keep going up and up and up. And so you add data, and voila, you get Lambda CDM. And so I thought I would do this in English. I think this is even tweetable under the new rules. All my teaching now is in tweets, and opening it up to 280 characters is, this might be, so Lambda CDM, I don't think anyone could have imagined, if you looked at cosmology in the 70s, if you interviewed people, that we would ever get a theory this expansive. So it describes the universe from a tiny fraction of a second when galaxies and larger structures were just quantum fluctuations, so I'm talking about inflation, to the hot lumpy quark soup, from quark soup to neutrons, protons, and then light nuclei, from ionized matter to atoms, photon mass scattering, from lumpy dark matter to stars and galaxies and large-scale structure, and I guess I should have put in accelerated expansion. So that's quite an accomplishment that I'm not sure that anyone would have imagined that would happen. The key features, and then I want to tag this to Gary's work, inflation. This big burst of inflation, this big burst of expansion that allows microscopic phenomenon to become impressed on macroscopic scales. A baryon asymmetry. So even if you read Gary's paper and said, okay, whatever, I just need a baryon asymmetry, the creator put one in, creator put in dinosaurs and all kinds of other stuff, so that's not going to be a problem. But once you have inflation and that enormous entropy release, getting the baryon asymmetry was crucial, and dark matter particles. Baryons aren't enough in two regards: to account for how much matter there is, and even if they were all the matter and there weren't dark matter, the density perturbations are not big enough to grow the structure that we see. Even someone as clever as Jim Peebles never succeeded in doing that. And then finally, the repulsive gravity of dark energy providing the bulk of the closure, the critical density, and leading to the accelerating unit. So those are the key elements. Let's see, I think I already said this. We've gone on this tour before. And there's data, and there's precision. So all of these words are backed up with data. Our poster child in cosmology for precision is the temperature of the microwave background. When I teach cosmology, the students have to get a tattoo with that number. Let's see, so the universe is flat to better than 1%. We know the matter, the baryons. I'll come back to the discrepancy here. Gary played a big role in this discrepancy between the total matter density, a little over 31%, and the baryon density, 5%. So that I can tell a story about cosmology and astrophysics. You know, in the good old days, in 1978, if for omega matter, 2 different methods gave 30% and 5%, you would jump up and down that they agreed. If they had the same units, you would be happy. And here's the dark energy. The Hubble constant we'll come back to. Oh my goodness, this is the problem with high quality data. So this is a slide I used a couple of weeks ago, and I did not update it for the 2 weeks of the age of the universe. And a lot of this comes from the microwave background. You all know that it's the surface of last scattering, that the universe earlier than about 500,000 years was ionized and opaque, and so we get to see the universe at a simpler time. And when we started talking about the data revolution, it would be hard to pick one event. You know, you might say that first redshift survey, CFA1, that no one remembers, that Mark Davis and John Huckra and Margaret Geller were actually, she wasn't involved in CFA1, but the microwave background, the COBE results that are shown here that were announced in 1992, seeing the fluctuations in the microwave background, and then WMAP, and then our best image of the microwave background is the Planck all-sky image that's just stunning. You know, if you're a cosmologist, I mean, this is the Rorschach for cosmology. You go into the psychologist's office, and they say, you know, what do you think of when you see that? And if you say, it makes my heart go pitter-patter, they say, you're a cosmologist. And then if you say, oh, it looks like Gaussian random noise to me, you go into the other line. So much of what we know about the universe comes from the microwave background. Of course, you know, they look like very big fluctuations, but if they're at the part in 10 to the 5 level, you know, 30 microkelvin. They're measured very precisely. And I think this is the part, if Gary didn't make this joke, he should have, is that in Lambda CDM there are 6 parameters. So you can describe everything we know with 6 parameters. In Columbus, Ohio, it takes 10 parameters to give phone numbers. Right, and I don't know if we do, you know, phone numbers for the world. How many? If you add the country codes, how many country? I forget what it is. But six numbers describe the universe from quantum fluctuations until today. And so you've seen the power spectrum, and this curve that goes through it is not something that was hand drawn by a theorist, but it's the best fit using those 6 parameters. And here's the polarization. Oh, and then we, you know, on the way, we did Sandage's bucket list. So H0 was measured. We'll come back to H0 with precision and accuracy. And Q0 was measured. And I don't know how many people have read the paper where Sandage defines Q0, where he carefully puts in a minus sign that's so hard to keep track of, because it's the deceleration parameter, and you would never want a parameter to be negative because it's, you know, there might be some quantum instability or something, and of course it is negative. And so this is a photograph of Einstein when he heard that the universe was, actually it isn't, but, Those have both been, and I just want to make a slightly different point. This is this recent Cook paper that argues that the deuterium has been measured to 1%, and Keith talked about this. I just want to make a different point here, actually two different points. So from BBN, from the deuterium abundance, you can figure out the baryon density. So this is the error due to the measurement of the deuterium abundance, and this is that theoretical error that was being talked about with the P gamma reaction. And so it's just slightly, this is about slightly smaller. And so that comes from nuclear reactions in the universe when it's 1 second old, roughly speaking, seconds old. From the microwave background, this is the number you get. And I want to say two things. Number one, they agree. And this number is based on entirely different physics. Gravity-driven acoustic oscillations when the universe is 400,000 years old. If you had asked David Schramm or Gary Steigman, you know, okay, when both of them knew that the microwave background, and Gary lived to see it, was going to measure the baryon density. If you'd asked them, you know, are they going to be close? Are they going to, you know, they differ, I can't quite read this, 2.5%. That is amazing. And when you think about all the tests of the framework, and then the last comment I want to make that, you know, is if you look at this error, that is smaller than that. So BBN is back in the driver's seat. So we, you know, we need to be talking about the microwave background needs to be comparing itself to the platinum standard. It may be the gold standard, but right now BBN is the platinum standard. So I think Gary would be very pleased about that. Oh, this just says that everything fits, lambda fits. So Gary played a pivotal role in this transformation of cosmology through his scholarship and through other activities where he seemed to be, I read this, maybe I wrote it in one of the obituaries, he was at every meeting. And he was, I don't think he was ever, Tom, was he ever at Bartol? I think I visited him there once, but.
Yeah, I was just remembering that he brought Holly in it when he took it down the hall to his office.
But he traveled a lot. He traveled a lot. So so I listed, you know, where he was, and couple of. This is a picture from his first postdoc in 1971 at Cambridge, and everybody recognizes Fred Hoyle, and Willie looks like what's that guy Bolger in Boston? Whitey Boston. And Gary looks like Gary, and they're at a pub in Cambridge, and so we've heard this mentioned earlier. He had this. Actually, this must have been when he went back during the summer. So in the olden days, in the 1970s, a rite of passage was to go to Cambridge for the summer, to Fred's Institute. And actually, that if I read these numbers correctly, and I think this is the right year, this is not when he was a postdoc, he went back for the summer ritual. Aspen, I'll have more to say about Aspen, workshops. So he visited Chicago for a year, and of course I mentioned inner space, outer space, and the group building. Okay, so let me talk about the papers. So no antimatter. So Paul Lanneker can probably testify to this. Particle physicists really wanted to hear this. They really wanted to know that you couldn't have a baryon symmetric universe. And they're pretty hard-nosed, and Gary satisfied them. And this all started when he was at Cambridge. Actually, it started with his PhD thesis. But he became In fact, I wanted to show something. I put some cite totals up here. Not that they mean that much, but only 23 citations to the Nature paper that I can't remember. I think it was Bob was talking about. And the reason he wrote this, the reason that he got on this hobby horse was Omnis and Alfvén had this baryon symmetric cosmology with Leidenfrost that prevented the annihilation. And Martin Rees was telling me about, and this will not sound like the Gary you know. Omnis, this distinguished French physicist, came to talk about his cosmology, and Gary gave him hell. You know, that's not the Gary we know. Okay. And then he wrote this annual review article some years later, and it was much more well cited. But this, I mean, at some level, especially, I mean, Nature's probably embarrassed by this paper because they only do high impact, and so they probably want to say, oh no, we never published that paper. But the high impact paper, the Nature paper, didn't really get that much attention. But it played an important role in convincing people that you needed to generate a baryon asymmetry. Here is a paper that I think is really important. And again, in fact, this is really why I put the cites up, because I'm going to tell a little story about it. This is called the neutrino-dominated universe, and I called this dynamical non-baryonic dark matter. And I've been to a couple of meetings where we talked about the history of dark matter and cold dark matter, and Keith wrote a very influential paper. Is it Ellis et al.? This is the one that laid out, here's the best bet range, 4 to 7, 6 is in there. If you use lithium, you don't, 6 is not in there. And this is the upper limit saying you can't go higher than some number between 0.14 and 0.19. The Hubble constant comes into play here. So this is the one that's starting to establish the linchpin for non-baryonic dark matter. In fact, I don't have a slide on this, so I'll just say it. That linchpin today, when you look at omega baryon h squared from BBN and compare it to omega matter h squared from the CMB, they differ by 50 sigma. So it's no longer about sigma. It's did you get the theory right, or is there some fatal flaw in the way that you're looking at things? But this is the paper that really started that. So we've, you know, I thought, how can I be polite here? And I thought, you don't have to be polite. And we talked about the Chicago groups and the, and so Keith reminded me of the Nicene Creed. Actually, Bob, tell us about the Nicene Creed.
What would you like to know?
So this is a very important document about belief, right? And the Nicene Creed, we heard about, let's see, Penn. We heard about the, you know, the difference between the Chicago group, the Mafia. I can't believe we're called the Mafia. You're gonna hear from my lawyer. But the Nicene Creed, difference between the two, and Bob, you're a scholar. Can you translate for us?
Yeah, that says lambda H.
No. So the translation of that, the Nicene Creed for the Ohio State group is the non-existent fake news deuterium bottleneck. And the number of years I tried to show, I mean, Gary actually was amenable to logic, and there is no such thing as the deuterium bottleneck. But I realized why he couldn't let go of it, because this is the Nicene Creed for that makes the difference between the two groups. Okay, so there it is. And then here's the paper, and this was really a fun paper, and I think Gary, I don't remember when we wrote it, but I do remember it does reflect a lot of Gary's sensibilities, because let's go to 1984, and inflation predicts a flat universe. There's no question about that. I mean, if you don't have a flat universe, you may as well throw away inflation. And if you're not an astronomer, you know that a flat universe means not that omega matter equals 1, that everything adds up. And so
we heard this already about Sherlock Holmes. When you eliminate the impossible, whatever's left, no matter how improbable, must be correct. And so already at this time, omega matter had risen from the 1970s, but it was beginning to top out. And it topped out a little bit later at about 0.3. And so what are you going to do? It can't be matter if it tops out. And so if you have this theory and you really believe into it, you have to have something else. And so relic cosmological constant was suggested here. So now let me segue to Gary's group build, to his influence in the field with workshops and the like. So this was a very important workshop. Somebody's going to say, you left out the K and you're a Kavli director. So this workshop was at the ITP in Santa Barbara in 1981. I think it may have been either the first or second workshop at the ITP. And Gary was in charge of it. And it was on the early universe. And it really brought everyone, this is the first time Rocky and I met and collaborated. And this is a product of our collaboration. We learned about making T-shirts and how much money you could make selling T-shirts at physics conferences. So this was a very influential workshop in early universe cosmology. We heard about Gary and Aspen, and I just want to say, sorry?
He's facing the other way.
I know, I've got both versions of that photo. I don't know which one is correct.
Yeah, I'm not sure which way he's, I noticed that too. But he still looks the same.
Well, he's left-handed, so I bet that's the correct one.
This one?
Well, he's left-handed, and he's holding the leash with his left hand.
Okay. Anyway, he spent 23 summers in Aspen. 1972 was the first. He's the person who actually introduced Dave Schramm to Aspen. And actually, while I'm up here, I want to say, so Dave and Gary were a great duo, like, Lewis and Martin, if anybody remembers Lewis. I mean, they were very different and complemented one another. 46 of Gary's papers were, how many did you write with Gary? 35. 46 of Gary's papers were with Dave, and half of his citations were on papers with Dave. And those of you who know Dave, we already heard it, Dave was not a detail guy. And the two of them worked very well together in the way that Italian sausage is a good product, right? There were, and I know Keith alluded to this, I'll be a little more direct. There were many times when Gary would be just fuming at Dave for, blah, 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 blah. But they really were a good partnership. Aspen is another place where Gary, and I'll jump down to the bottom, he helped to organize workshops there. And so that was one of the places where this field got going. And in fact, Gary was among the pioneers in the very beginning. I forget what the first summer at Aspen was. I think it was 1963. And they didn't have astrophysics. And Gary was among the group that brought astrophysics there. And the first NASA workshop where they got money, it's very funny. The title of the workshop was The Physics of the Early Universe. And I should have brought the program, but it's not the early universe that Keith and I and Bob are thinking about. I mean, it's like redshifts of 1 or 2. But Gary did talk about the Hadron Era, and this is a collaboration he had with Steve Frauci and John Bacall. Again, this is in the time where we hadn't quite accepted that quarks were the high temperature degree of freedom. This is a workshop in the summer of 1983 on cosmology and monopoles. You may remember the monopole that was discovered on Valentine's Day. I think it was 1982, so this might have been. And let's see, there's Katie Fries, Alan Guth. Can anyone not pick out Gary? Pierre Ramon. Can anyone pick out Rocky? There's Rocky looking like an Arab terrorist. The young John Rosner. Anybody recognize that? Sid Bloodman. There's Neil Turok. What was interesting about that summer, oh, there's Dave Schramm. What was interesting about that summer was Neil had his PhD examination in Aspen. I don't know who, this might be Andy Albrecht. There's Paul Steinhardt, and I don't know who that is.
This guy on the far left in the plaid pants.
Sorry?
Like his fashion style. The guy on the far left in the plaid.
Oh, you know, Grano is his, he's an Israeli.
Oh.
Grano, yeah, you know him. Yeah, actually, he looks the same as he does today. Okay, but so this is, I'm winding down here. I'm essentially done. So this is the same slide I showed you earlier. So this is a great model, except the four basic elements in it are all invented. They're not part of the standard model. And so these are opportunities for discovery or, you know, proving that this was fake news, to use the modern vernacular, for disruption. And so, you know, I thought I would imagine asking Gary his opinions on where things are going to go. And of course, we'd really have to tease it out of him because, you know, he was reluctant to share his personal views on, you're supposed to be laughing at that. So, you know, actually the controversy, this is Alan Sandage's revenge. So, you know, it is the most important parameter in cosmology, in spite of what, you know, we invaders from the physics world say. And this is a chart showing measurements using the microwave background and the assumption of Lambda CDM, and measurements that use direct measurements use the infamous distance ladder. And there's more than a 3 sigma difference between the two. And of course, they both could be right. I mean, that's what's exciting about it, is they both could be right because one is making a direct measurement and the other it has an assumption. Or they both could be wrong, or one of them could be wrong. So we asked Gary, and he said the CMB right, astronomers have a bad track record for being able to measure anything. And well, it's hard to argue with that. I mean, he cuts right to the core. Cold dark matter, this was a struggle. As we talk about Trump, you know, I love the New York Times says, you know, truth is a struggle for, and cold dark matter was really a struggle for Gary. And but he was a pragmatist because cold dark matter, I don't know how many times it's died. And each time it was dying, Gary was so happy because he loved hot dark matter. And so I think on cold dark matter, he's probably rooting for one of these alternatives. I'm not even going to talk about them. Baryogenesis, I think he would be disappointed that we still haven't figured it out yet. I know he would be disappointed. I know back in 1979 when Rocky and I were working on baryogenesis, he kept saying, but can you calculate that 10 to the minus 10 number? And of course, we're a long ways away from that. But I think he'd be rooting for neutrinos and leptogenesis. Inflation, I think he bought into. The lithium-7 controversy, I wasn't, you know, his colleagues know more about this than I do, but I have a feeling this was bugging him. It is not, you know, in spite, Keith is great. Don't tell him I said this, you know. You saw the hand waving and the, yeah, don't worry, Keith, I'm not. But this really is a nagging, it's a factor of 2. And Gary's most cited paper uses lithium to get the baryon density low by a factor of 2. We got to get the lithium straightened out. And it's not going to be easy. I mean, I thought Mark did a fantastic job of talking about the astrophysics of it, where you kind of have a story and bits and pieces are definitely true, but then there's some counterfactuals. I mean, I think Gary would be dark energy. I think he would say, like I said, it's lambda. Imagine that New York voice, and I added the multiverse here. I don't think he was, wouldn't he say, get out of here? This is,
bogus.
yeah, bogus. Bogus. Let's see if I think that's, I don't have, yeah, no, that comes from another talk. I think that's a good place to leave it. So Gary really played a major role in this revolution that brought us to where we are. And I just want to come back to Alan Sandage. No one, Jim Peebles, no one would have imagined in 1975 that we'd be where we are today. I mean, things were so gloomy back then in terms of, well, I think it's gravity for structure formation, and there's adiabatic and isothermal, and then you got the spectral index, and I think it's amazing where we are. But for the students, going back to this slide, it's all built upon things that haven't been discovered. And so I think that's the exciting part. And you can look at it two ways. Either you discover things or you pull apart this picture. Thank you.
Questions for Mike? No questions for Mike? Oh, Julie?
The comment, I was chuckling to myself when you were talking about the lumpy quarks and with lumps of order 10 to the minus 5. We now know about lumpy quarks with the heavy ion collisions.
Yeah.
Density contrast the factors of 2.
Yeah, no, this is, when you look at the microwave background, I forget the analogy, but it's smoother than most ball bearings. It really is remarkable how smooth things were. No rebuttal on the deuterium bottleneck.
I don't buy into that anymore. I have my own.
Yeah, actually deuterium was overabundant, but yeah.
Well, I just like to endorse really what you said, Mike. I mean, I was involved with Sandage. I remember the paper of the search for two numbers and his view of the universe, of course, from working with him. But I think you're quite right. It was nice the way you ended in 1975. You're right. We had no clue this was happening. And on the positive side, it's just been an incredible progress that we've gotten to where we are. So that it's been really an exciting time when our view of the universe really has changed. And, it was, I personally didn't appreciate how much Gary contributed to this because I was working in different areas. I didn't appreciate it until, after I got here and so on. But I think it's very timely. And I think you put on the future now where it is. So I just want to endorse that and thank you for saying all that.
Thank you.
Grant?
Oh, I'd just like to hear your version of the food fight.
Well, actually,
I saw that. So I saw the food.
yeah,
So I was there. There was.
I was at the meeting, but
Should you want to? I mean, do we want to hold this or should I?
Save it for lunch.
All right.
yeah, okay.
Okay, so it sounds like John is hungry.
well, so could I have the last word on this?
Sure. Take it anyway.
Which is correct. So I just wanted to end on a very positive note that the Chicago school and the Gary school and I think that everyone had a place and got along well and had different skills. And I would bring it back to Dave and Gary. And those who knew both of them, they had very, very different styles. And Gary, maybe church lady is not quite the right word, but everybody had a slightly different role to play. And Gary's connection to real astronomers was really critical. He had credibility in that community. He was a professor of actually he was only an assistant professor of astronomy at Yale, which is a whole nother story. But I think that maybe there were some creative tensions, but there was a personal warmness and exchanging of students and postdocs and educating people. And I think Keith would probably say this, that, oh my God, you don't just want to be mentored by Dave Schramm. You need a little, reality, whatever you would call it, that adding that Gary mentoring where you have to exchange handwritten letters, and you actually really do have to get numbers right. You can't, and the English language matters. And so I think I would like to just add, I'm sure both Bob and Keith were speaking, good-naturedly about this tension. It was, I think, the kind of healthy tension that you see among people who work well together and respect one another and just have different styles. And I'll finish by quoting Sidney Coleman, who many of you know. Sidney would explain the different styles and tastes by saying, thank God everybody has different tastes, otherwise everyone would be chasing my wife. And so if you think about it, variety is important. Sorry, Doug.
Oh, that's fine. Perfect ending. I don't remember where we're going for lunch, John, so maybe you want to remind people. I know the general direction. I mean,
Let me first join Terry in thanking all of the speakers and everybody who came. Thanks.